body serves as a role model for designing the next generation of robots. With the advancement of artificial intelligence, today's robot can perceive their environment and make decisions, much like the functionality of our brain. But we also have an advanced physical body with incredible properties, such as self-healing. When we get a small damage, without us even thinking, it heals. What about robots? Robots are not just in factories anymore. They are becoming part of our daily lives. For close, safe and adaptive interaction with human and the delicate objects in our environment, robots in many cases can no longer be made out of metals, or at least not fully. They require soft, flexible and stretchable materials, much like those found in natural organisms like octopus, elephant trunk or our skin. Soft robotics focuses on developing robots that are made from soft materials. They can move more naturally, like bending and twisting, and they can provide a safe and adaptive interaction with their environment. While soft materials can handle shocks well, they can be damaged by sharp objects or stretched too far, just like biological soft tissues. The solution again lies in nature. In collaboration with our polymer group, we have developed self-healing materials based on Diels-Alder reaction. These are dynamic covalent bonds that can break upon mechanical damage. But upon recontact, and due to their reversible nature, they can reform and create new bonds. In many cases, this process is stimulated by a heat-cool cycle. Raising the temperature breaks more bonds and increasing the network mobility. Cooling allows them to reform, enabling healing across the damage. But the reality was that self-healing in robots was far from reliable, and in many cases, human intervention was required to ensure successful healing. This is because these self-healing materials are synthetic, so they cannot grow. And in most cases, they require external stimulation for healing. On the other hand, robots were not truly designed to take the full advantage of this material property. Healing is not only a material property, it's a process. In our body, healing is supported by multiple mechanisms. I studied different phases of a self-healing process and innovated healing-assistive mechanisms to ensure self-healing without or with less human intervention. First and foremost, robots need to feel pain. They need damage detection sensors. To achieve this, we need to develop a property that can be measured and that changes upon damage. I accomplished this by making the self-healing materials electrically conductive through the addition of carbon black particles. When damage occurs, the conductive pathways are disrupted, increasing electrical resistance, which we can measure. But I aimed for more than just detecting damage. I wanted to localize it to enable targeted self-healing actions. I designed a flexible electronic skin with 4 resistors. By carefully modeling and optimizing the circuit, I found a unique ratio between 4 resistors, ensured that each damaged pathway causes a distinct equivalent resistance change, allowing the system to pinpoint the damage at 4 zones with only 2 measuring electrodes. After damage detection, one crucial phase of self-healing is closing the gap. As mentioned, self-healing materials cannot grow. As a result, upon damage, often a gap or incision is created that must be closed for self-healing to occur. To address this, I came up with the idea of using shape memory alloy wires, also known as muscle wires. When the temperature increases, these wires shorten in length, providing a mechanism to pull the damaged surfaces together. I integrated these wires into fiber-reinforced actuators, which are commonly used in soft robotics. These actuators are made by wrapping fibers, like nylon, around the soft chamber. So when the chamber is inflated, it bends, stretches, or twists. Instead of using standard fibers, I use shape memory alloy wires. While these wires are not self-healing themselves, they are highly damage resilient, making them ideal for this application. After damage detection and closing the gap, the next phase is stimulating the material for the actual healing, often by increasing its temperature. Previously, this was done using external ovens, which are bulky and require heating the entire robot. My solution was to innovate a self-healing heater that can be embedded directly into soft robots, enabling localized heating. This was achieved using conductive self-healing materials, similar to the materials used to make the damage detection sensor. I developed a thin film of this material that generates heat via Joule effect when electrical current passes through it. Moreover, when the heater is damaged, the resistance is locally increased, so the heat is naturally concentrated at the damaged area, providing localized heating and healing. If the system has healed properly, the resistance should return to its initial value, or the heat distribution should be uniform rather than concentrated at a specific location. This means that by monitoring the resistance of an electrically conductive self-healing material or analyzing the temperature distribution, the robot can gain information about its own health as one of the final self-healing phases. Health monitoring has different aspects. One can be the recovery of the material fracture properties, and another one, the recovery of the material or the robot's mechanical stiffness. As for healing, temperature increase is often necessary. This causes the material to be softer. And in many cases, it takes several hours until the material or the robot recovers its initial stiffness. This long recovery is of course not acceptable for many applications. In my collaboration with Festo, a leading automation company, I integrated the self-healing technology into one of their commercial gripping tools. I developed the Vrije finger from self-healing materials, and to accelerate its return to operation after healing, I introduced a variable stiffness scheme. This variable stiffness scheme consisted of a self-healing chamber attached to the main finger. Inside the chamber, I placed thin layers of sandpaper. When vacuum was applied, these layers compressed together, significantly increasing stiffness. This allowed the gripper to actively compensate for the softening effect caused by heating during healing, restoring its ability to apply the same force as before damage. Thank you very much for listening to me. This was a short summary of the main projects of my PhD. I would like to thank European Union for funding me under SMART and Shinto projects. As the last comment, I believe the future of robotics isn't just about advancement in artificial intelligence. Robots also need a more advanced physical body. As human, our body is multifunctional, adaptive, and resilient, allowing us to sustain in a constantly changing environment.